Good afternoon, dear students. So, in the last class, uh, we have seen the various type of dampers which are used. Apart from all the four dampers, the viscous damper, that is also known as viscous dampers, and the dry dampers, okay, or dry damping, that is also known as Coulomb damping. So these two types of dampers are very much important in terms of our undergraduate course. So in the last class, we have analyzed the spring mass system, that is a single degree freedom system where there is a damper. Okay, so I just want to repeat the same thing. Yeah, so this was a single degree freedom system, that is a spring mass system where we have attached this damper or this dashpot. Okay, so this dashpot is having a damping coefficient C and it is displaced. So what we got in the final equation of motion, that is mx double dot plus cx dot plus kx equals to 0. So this was the equation of motion for this damped free vibration of single degree freedom system. Okay, so till now we have not introduced any external force. That is why it is also a free vibration. Okay, so it is not necessary that wherever there is a damper, there will be a force vibration. Okay, so this is completely a free vibration analysis. So this equation is a second order differential equation because mx double dot term is there. So for this kind of equation, differential equation, the general solution, it is given by x equals to e to the power s t. Okay, so small s t. So where s is a constant, so which needs to be determined. Okay, so we will be finding out x dot velocity and x double dot, that is the acceleration from this expression, and we put the values x dot and x double dot value in our equation of motion, basic equation of motion of a damped free vibration of a single degree freedom system. Okay, so what we got m a square e to the power st plus e sorry, because cx dot, this is c, small c. Okay, so c s e to the power st plus k e to the power st. Okay, so if you just make e to the power st common, then you need to write like this: m square plus cs plus k equals to 0. As because e to the power st, it is having some definite value. Okay, because we have assumed that the solution to be x equals to e to the power st, that is why it should not have the value equal to 0, because x is the displacement, isn't it? So there is a finite displacement value, so that means e to the power st will be having some finite value. Okay, so that is why the bracketed term must be equals to 0. Okay, so here this is a quadratic equation, and this equation is also called as characteristic equation. Okay, for this complete equation, this is the characteristic equation, and this is a quadratic equation also. So solution of this equation is found out by this way: ms square plus cs plus k equals to 0. So s will be equals to minus b plus minus b square under root b square minus 4ac by 2a. Okay, so if you just use this formula, okay, to find out the radicals, so your final expression will be this one. Okay, so s12, because this is a quadratic equation, is in s, so there will be two values of s. Okay, small s. So s12 will be minus c by 2m plus minus under root c by 2m whole square minus k by m. Understood? So don't be confused why this equation becomes this one. Okay, so actually these are the two roots of this equation, quadratic equation. Now our solution was e to the power st, x equals to e to the power st. Now we have got two values of e to the power st. Okay, that is why we will be writing the final solution as x equals to c1 e to the power s1t plus c2 e to the power s2t. Okay, so we will be writing the general solution as this one. Okay, so where c1 and c2 are the constants to be determined. Okay, so these are arbitrary constants. So we will be finding out this value because we know we should know the solution. Okay, final solution of this type of damping system. So how we are going to find out the solution? So first we will be defining two terms. Okay, so one is cc, okay, small c suffix small c. Okay, so that is called as critical damping coefficient. Another one is damping ratio, that is zeta. Okay, so zeta, so just like e. Okay, so one tail will be there and one small head will be there, so zeta. Okay, so just like epsilon, so you will be able to write, so one small head will be there, one small tail will be there. So this zeta, 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 these are constants. Okay, so just like your Greek letters. Okay, Greek terminologies, not terminologies, Greek symbols. Okay, so what is cc? So how it is actually taken? See, this radical c by, okay, c by 2m plus minus under root this term, under root the term which are under root. So c by 2m whole square, okay, minus k by m. So that means what? K by m is what? Omega n square. For a single degree freedom system, omega n square equals to k by m, isn't it? So if we can write some term, okay, if we can introduce some term which is exactly equal to c by 2m, then this radical sign will vanish, isn't it? Because 1 minus 1 will be equals to 0. That means x minus x will be equals to 0. That means this radical sign will vanish. Okay, so what we will be doing, we will be writing one equivalent terminology which will be equivalent to this k by m. Okay, so how it can be written? So now we will be writing one terminology. Yes, okay, we will be writing one term which will be cc by 2m. Okay, cc by 2m, what is this? This is c by 2m, isn't it? So we will be now writing cc by 2m, which will be exactly equals to k by m. Understood? Which will be exactly equals to k by m. So why we are writing this instead of k by m? Because instead of this k by m, if we will write, so this terminology, okay, may vanish. Okay, so which will simplify this solution. Understood? So c by 2m minus whole square minus k by m, isn't it? So instead of this k by m, so what we are actually writing, cc by 2m. Okay, so cc by 2m whole square will be equals to k by m. So we have assumed. Okay, so this cc is called as critical damping coefficient. It is written like this. In order to proceed further, it is desirable to define a new term called critical damping coefficient, denoted by cc, and cc is basically written cc by 2m whole square equals to k by m. Okay, so this is written with respect to this expression. Understood? Now this cc by 2m will be equals to what? Under root k by m. So what is under root k by m? As I have told you, this is natural frequency of this system. Okay, so now we will be defining another dimensionless factor, zeta. Okay, so I have told you that this zeta looks like this one. Okay, one small head also you can introduce here, but it will be a small epsilon and one tail will be there. Okay, so this is dimensionless factor zeta, called the damping factor, okay, or the damping ratio, damping factor or damping ratio. So may now be defined as the ratio of the damping coefficient to the critical damping coefficient. So zeta will be equals to c upon cc. So what is c? C is the damping coefficient. Okay, damping coefficient we have taken here as damping coefficient small c. Now another terminology, cc it is taken. So cc is c by cc will give you this dimensionless constant, that is called as zeta, zeta, zeta. Okay, so now we will be introducing these two terms, okay, cc by 2m or cc and this zeta in this expression, okay, so that this expression becomes simpler. So how we will be now introducing this one? So cc has got characteristics like it depends on mass and stiffness of the system. So you need to remember actually these points. Okay, so in competitive exam these questions are basically asked. Okay, so cc basically depends on the mass and stiffness, because these are the two basic properties of a vibratory system, mass and stiffness. Otherwise the system will not vibrate. And cc is independent on actual amount of damping. Okay, so in just you should remember this is important point. cc is independent on actual amount of damping. Okay, it does not depend on c. So this in this equation c by 2m, now you see this expression c by 2m, isn't it? C by 2m term is there, that is why we are defining cc. So c by term 2m we will take. So c by 2m can be written like what? C by cc into cc by 2m. Okay, so it is also correct because we are writing cc extra, that is why we need to introduce cc in the numerator, isn't it? So c by 2m is already there, so cc and cc we have introduced. Okay, so what is c by cc? So c by cc we have defined as zeta. So this is the damping factor or damping ratio. Okay, so in some in exam it is asked that what is a damping factor or damping ratio, that it is the ratio between the damping coefficient to the critical damping coefficient. Okay, so here instead of c by cc, so we will be writing zeta, and instead of cc by 2m, so we will be writing omega n, because cc by 2m equals to what? Omega n. Now this expression will become, this expression, these roots of S12 will become like this way. So S12 minus zeta, because minus c by 2m was there, so minus will be remain minus. So c by 2m instead of c by 2m, so we will be writing what? Zeta omega n. So c by 2m will be zeta omega n. Okay, so omega n it is there, plus minus, because plus minus symbol is still there, plus minus. So c by 2m, so what I will be writing here? Zeta omega n square. Okay, so omega n will be taking out, so zeta square will be remain there, minus. So what is this one? K by m, so it is omega n square. Okay, so if you take omega n square, only 1 will be remaining here, isn't it? So 1 it is written. So the two roots becomes in bracketed minus zeta plus minus under root zeta square minus 1, so bracket close, into omega n. Okay, so this is the root for this single degree freedom system of a damped free vibration. Understood? So here, so basically three conditions actually, so we generally take in damped vibration. So here you can see, if zeta is what? This is the ratio between c and cc. So if c greater than cc, okay, means damping coefficient is greater than cc, then what will happen? The zeta value will greater than 1, isn't it? So if numerator is greater than this denominator, so if you divide, so it will be having value greater than 1. That means zeta greater than 1. Okay, so this type of damping motion, it is called as over damping system. Understood? So when the value of zeta is greater than 1, so this type of vibration is called as over damping vibration. Understood? So when c equals to cc, so then zeta value equals to 1, because c numerator is equals to denominator. Understood? Okay. Now if c less than cc, so it is also possible, then zeta less than 1. Okay, so from this expression, if c less than cc, so this part will be greater than 1, that is zeta less than 1. So it is called as under damping condition. Understood? So under this three condition, so now you need to find out this value of this s. Okay, means the roots of this characteristic equation. So under this three condition, means first we have taken one small equation, okay, one small equation, differential equation. After that we have found out this general solution, x equals to e to the power st. Then finally we have got these roots, okay, and we have simplified these roots in terms of zeta and omega n, okay. So zeta and omega n we have introduced, and finally we have got this expression of the roots, okay, s12. And from this expression, so what we have actually summarized, that if zeta value greater than 1, under damping. These three lines are very important in terms of exam point of view, okay. Any exam, competitive exam, any exam, gate exam, okay, always there will be one question, okay, in alternative year actually. So these questions are asked, okay. Sometimes it is asked as critical damping, sometimes it is asked as under damping. So like that it is asked, okay. And you should know this conversion also. So c by 2m, how it is zeta into omega n, because in the question this value will be given and you will be asked to find out the mass, okay, if c is also given. So like that these type of questions are basically asked, okay. Objective type questions are basically asked. Now what we are going to find out, so we will be solving these roots, okay, values of these two roots in each of these damping system, means in over damping, in critical damping, and in under damping. So up to this much. So if you have any doubt, so you can ask. Okay, now let's move. Okay, now let us take this over damping system. Okay, I think the letters are visible. Yes. So in over damping system, so I have told you that zeta value is greater than 1. Okay, so if you put zeta value greater than 1, so what you will get, you will get two values, because s12 equals to minus zeta plus minus zeta square minus 1 into omega n. So if zeta value is greater than 1, that means we can write zeta square minus 1. If zeta value less than 1, then we need to write 1 minus zeta square, like that, okay. So we are writing these two roots separately. One will be plus, one will be minus, okay. So minus zeta and plus zeta square minus 1 omega n, and similarly we are writing this one. So if yeah, so here you can say that this value of these two roots, okay, two roots are real negative numbers, because see, this will be some positive number, isn't it? So this will be some positive number. So minus zeta, okay, so which value is greater than 1, so plus some smaller value, so it will give you the negative value, isn't it? So here also both the signs are negative, isn't it? So what you will get, so s1 will also be negative and this one will also be negative. So both are real negative numbers, isn't it? So s1 and s2 are negative numbers because zeta is greater than 1, okay. So the solution of this kind of roots for the differential equation, which was x equals to c1 e to the power s1t plus c2 e to the power st, was the solution, is given by x equals to, so the same expression what we actually got in the last derivation, okay. So this was the last solution. So as because the roots are real and negative, that is why you can write a solution in the same way, okay. So here we will be putting s1 value and s2 value what we have got, okay. So we will be putting s1 value as this one and s2 value as this one, okay. So c1 e to the power, c, the complete s1 value I have written, 1 omega n was there, so c1 e to the power s1t, so t will also be introduced, plus c2 e to the power s2t. So instead of this one s2, we will be writing the whole expression. Okay, minus zeta minus under root zeta square minus 1 omega n bracket close t. Okay, so we have given it number 6. Okay, so this is the solution of this overdamped system, isn't it? Overdamping system, because zeta is greater than 1. Okay, so now we need to find out this value of C1 and C2, because these are the two constants to be determined, isn't it? So how you will be able to find out the two values of these arbitrary constants? So now we have to apply the boundary condition or the initial condition. Okay, just do it. Okay, so we'll be using that initial condition just like the previous derivation. So at x equals to x naught means some initial displacement was there, x equals to x naught. This is x naught. Okay, you can say that this x was x naught when t was equal to 0, means when you have started your clock. So at this position it was x naught, x equals to x naught. That x naught is not written, so you just you can write it here, x equals to x naught. So when t equals to 0, and the velocity, initial velocity, there was no initial velocity, that is what x naught equals to 0 as t equals to 0, means when the vibration was started, so there was no velocity. Okay, because this is free vibration, isn't it? And the initial displacement was x naught. Okay, so in free vibration the initial displacement is given as x naught. After that the body will start vibrating. Okay, so t equals to 0. So what we will be doing now, we will be differentiating, because we have got the value of x dot, isn't it? Or x naught, you can say x dot. Okay, x dot velocity. So now we will be differentiating this x with respect to t. Okay, then we will be finding out the velocity, because this is the equation with respect to t. Okay, and this is this is the expression with as displacement expression. Okay, so we are going to find out the velocity expression. So dx by dt will be what? So c1 will be remain same, so this will comes out e to the power st is what? So s e to the power st. So this will comes out minus zeta plus under root zeta square minus 1. Then omega n will also comes out, then e to the power, again we will be writing this expression, this one bracket term omega n t plus c2. Okay, so c2 is a constant, so c2 will comes out. Then this one, this bracket whole bracketed term multiplied omega n will come out. Okay, so this whole bracket and omega n will come out. Then again e to the power s to t. Understood? So that will give you the second differentiation. Okay, x dot, not second year, first differentiation, because this is x dot. Okay, so we don't need to find out the second derivative or second differentiation. Okay, now what we will be doing, so now we have got two equations, one is this one, another is this one. So here we will be putting the condition of displacement, because this is in terms of x. So at x equals to x naught, when t equals to 0, so we will be putting x naught instead of x. Okay, so now we are putting x naught instead of x, and we will be putting t equals to 0. So if you put c1 e to the power something into 0 will be equals to 0, so e to the power 0 will be equals to 1. So c1 plus c2 e to the power 0 means something into 0 will be equals to 1. So x naught will be equals to c1 plus c2. So the whole expression will convert it to this simpler form, x naught equals to c1 plus c2. Now in the second expression, that is in velocity, x dot, in x dot we will be putting the value of x dot equals to 0 when t equals to 0. So x dot will be equals to 0. So in the left hand side we have written x dot equals to 0. So instead of this t, we will be putting 0. Okay, so c1 will be there, this term will be there, bracketed term will be there, omega n will be there, and e to the power 0 will be equals to 1, means c1 and the bracketed term plus c2 into bracketed term. Okay, because this will be equals to 0, so omega n will be remain here. So now if you just simplify, so what you will get, so here c, so c1, okay, yeah, so omega n, because there is 0, so you can just cancel it out, because omega n it is not equals to 0. Okay, so that means what, this, the natural frequency cannot be equals to 0, but as because this is common, so you can cancel out, isn't it? So omega and omega n, because there is 0, so it is cancelled out. Only this term it is remained here. Okay, so C1 and this bracketed term plus C2 plus bracketed term, if you just rearrange like this way, so you will get this expression. So we'll be doing this one. So 0, then C1, then minus zeta plus zeta square minus 1, we'll be writing plus x naught minus C1, because x naught, yeah, C2 is what? C2 is what? From here, it is x naught minus C1, isn't it? So from this expression, you can write the C2 value. So instead of the C2, I am writing here x naught minus C1. Okay. So from this expression, you can replace this C2 by C1, x naught minus C1. Then again, we will write this one minus zeta square minus 1. Now you can simplify. Okay. So C1 minus zeta, and you can see C1 under root zeta square minus 1, and here C1 minus minus plus, so C1 under root zeta square minus 1, so 2 C1 zeta square minus 1, so 2 C1 zeta square minus 1, then minus x naught into zeta, so this one you have written. Now you need to write minus x naught zeta square minus 1, understood? This C1 zeta and C1 zeta will be cancelled out, because this is plus, this is minus, this is plus, minus minus plus. So only this much of it will be left. So when you will simplify, so you will be able to get this line, okay, very easily. Okay. Now from here, what you need to do, so x naught and x naught, so you can make it common, x naught, and these are minus. So if you just take it in the left side, so x naught zeta will be there, so plus under root zeta square minus, okay, zeta square minus 1. Now you will be able to write 2c1 under root zeta square minus 1. Okay, so now we will be writing the value of c1. So c1 value will be this one, and this is the expression which I have written here. Okay, so this is the expression which you will get after doing the simplification in this way. Okay, so the simplification is also written here, so you won't find any difficulties, just you need to practice. Okay, otherwise in examination you will forget everything if it is asked. Okay, so similarly the value of c2 will be like this, because this is plus, so this will be minus, so other things will be remain same, plus zeta square minus 1 x naught 2 under root zeta square minus 1. So you can do this one also. Okay, so it is a homework for you. So just like c1, so you need to find out c2 value, understood? So here instead of c1, you will be able to write down this c2 value x naught minus c2. Okay, so just put it this way and you will be getting this value as this one, understood? Okay, so now these arbitrary constants c1 and c2 are determined. Okay, now we will be putting this c1 and c2 value where? In this equation, in this equation. So x equals to, instead of this c1, so we will be putting that value or expression what we have achieved, or instead of this c2, so we will be writing the same expression. Okay, we will be writing the same expression what we have got just now. Okay, so only we will be replacing those things. So x naught by 2 under root zeta square minus 1, it is common to both these terms c1 and c2, that is why x naught divided by 2 under root zeta square minus 1 we have written here. So all this term now we need to write in bracketed form. Okay, so this is very simple. These things are very simple, only you need to make it common, because c1 and c2 are attached to both the terms, isn't it? So here you can see c1 and c2, so it's because these are common, so you have taken it common, so under bracket, so you'll be writing it this way. And if you just plot the value of x by x naught, okay, so if you just make it dimensionless equation, x by x naught, so if this x by x naught is plotted with respect to omega and t with different values of zeta, okay, so you will get this kind of curve. Okay, so x by x naught, what is its maximum value? Its maximum value is 1, isn't it? So this x naught can be only equal to x naught. Okay, so x by x naught this value will be 1 xm value. So from 0, 0.2, 0.4, 0.6, 0.8 to up to 1 we have taken, and here, okay, this omega and t up to this 5 units, so we have taken. So what you will get, so for a here zeta value, it is infinite. Okay, so this means what? So if zeta value is infinite, so the body will vibrate. Okay, so infinitely. Okay, so the body will vibrate in infinitely. So as when the zeta value is 1, okay, the system will be little bit stable here. Okay, so it will come to a stable condition. Okay, because the displacement ratio, it is nearly equals to 0. Okay, means there will not be any displacement. That is why, so here you will get a stable curve, okay, or a stable motion. Understood? So as you are increasing the zeta value, so this curve x by x naught with respect to omega and t, so it will be fluctuating. So if you just increase the value, zeta equals to 1, zeta equals to, zeta equals to 5, just like if you increase, so it will deviate away. Okay, or this vibration will be uncontrolled like this. Understood? So this is the expression, or this is the representation of this equation, okay, in terms of graphical form. So you need to remember this one. Sorry, this is called as displacement time plots over overdamped and critical damped system. So critically damped system, so we will be completing it in the next class. So up to this one, so zeta equals to 1, zeta equals to, zeta equals to 5, because all these are overdamping system. Okay, so how this displacement time plot will vary with respect to omega and t, so you should know all these firm lines. Okay, not this dotted line, because this is critically damping system, so we will be covering it in the next class. Understood? Yeah, so it is aperiodic in nature. So we'll come to that point, aperiodic in nature, that property. So you should know up to this much for today's class. Okay, so you should know up to this much. So you just practice it in your copy. Just you just note it down all these things. Okay, and do it by yourself. First you just take a look. Okay, how these expressions are written, and finally you just apply the initial condition, and you will get the value of C1 and C2. Now you will be putting those C1 and C2 value in the equation of general solution, and you will get this expression. Okay, so this is the general expression, or this is the final expression, final general expression of motion of a overdamping system, and for a undamped, for a damped free vibration single degree freedom system. Understood? So this is the equation, and this is the graphical representation. Okay, this is the graphical representation of motion in between this displacement, dimensionless displacement plot, and with and omega and t. Okay, so because this is dimensionless, x by x naught, units are same. Okay, so it is called as dimensionless plot. Okay, thank you, dear students, for listening. So if you have any doubt, you can ask me now.
Sir, hello, sir.
Yeah, Manas.
Sir, experiment number 2, I have some doubt regarding the lab, sir.
Or Manas, please wait. Okay, just I am asking doubts about this theory. Okay, I will come to that point later.
Okay, sir.
Okay, so for this class, do you have any doubt, Manas?
No, sir, no.
Okay, anyone? Yeah, okay, ask me, Manas. Yeah, others, if you don't have any doubt, then you can leave the meeting. Okay. Yeah, Manas.
Sir, তাতে K theoretical আৰু K actual এটা আছিলে, sir. Sir, সেইটো
কি আছিলে এক্সপেৰিমেন্টটো, কি আছিলে কোৱাচোন?
Sir, experiment to, sir, natural frequency of compound pendulum, to determine the natural frequency of compound pendulum, sir.